So this is our fourth lecture on Rankine vapor power cycles. Basically, we started with Carnot, then we moved to Rankine, and we talked about superheat, we talked about reheat, and now today we talk about regeneration. I think the terminology is a little confusing. I think superheat's pretty easy to understand. You don't stop coming out, as you come out of the boiler, you come out superheated vapor, not just saturated vapor. Reheat's easy. Okay, we're going to expand and then maybe take it back to the boiler for more heat added to the steam and then go through another turbine stage, so have two turbine stages. But the first time you see this word regeneration or regenerative Rankine or regenerative vapor power cycle, you may be at a loss. You probably are at a loss. It's not that clear. It's a little confusing. But we already know how to improve the thermal efficiency of a vapor power cycle. We know, especially from Carnot, the big equation. If there was one equation out of thermodynamics other than the first law and second law, it would be the thermal efficiency is 1 minus TL over TH. For a heat engine, Carnot, maximum efficiency. What does that say if you want a large thermal efficiency? What should you do to TH? Get it as high as possible. And what should you do to TL? Get it as low as possible. So you have a large delta T. High temperature at which you bring heat in, low temperature at which you throw it out. So when you look at superheat and reheat, they're trying to focus on getting a lot of heat in at very high temperature. You can look also at trying to reduce TL, but you're kind of stuck there. You have to dump it to lake water, and the lake water is not going to be dramatically different. Usually they build big lakes. Anybody around here been on a lake where they fish and the lake actually was man-made? I think there's one lake in the state of Texas that's not man-made. The rest of the lakes in Texas are all man-made. And a lot of them are made, well, for flood control, but a lot of them are made for power plants. And so what happens is they put in warm water one place. They usually have a little separation zone and make the lake large. And then the water has to go around before they could take it back out of the lake. And maybe there's a pump station to keep the lake at constant level. At Bay City, there's a nuclear power plant. They pump it out of the Colorado, or they have runoff, the rivers. But often they make sure the lake water stays pretty constant in the power plants for the lakes there. Anyway, you're stuck here, but you can still attack right here. So superheat and reheat made where you bring in the heat transfer into the working fluid at high temperatures. What about this regeneration? It's the same approach right there. What did we know was wasteful in the current system? It was, well, let me do this. Yeah. So from memory, can we sketch a power plant that has reheat? Okay. So we're going to have the steam generator or boiler. We'll have the first turbine stage. We'll have the second turbine stage. We'll have the condenser. We'll have a pump. And the fluid goes like that. So how does it go? It goes out of the boiler to the first turbine. We're going to reroute back to the boiler for reheat. Then into the second turbine. Out of the second turbine to the condenser, out of the condenser to the pump, and then the pump back. And why do I try and make a big deal about this is a particular Q on the first pass, and this is a particular Q on the reheat pass? Because students will forget the reheat pass, right? Okay, now, we have a good idea of the numbering of states. Let's put 1, let's put 2, let's put state 3, state 4, state 5, and state 6. And we could put this on a temperature entropy diagram. And if I put a line of high pressure Then I put a line of intermediate pressure. Then I put a line of low pressure. Looks like that. Where is state 1 if you have it superheated? Then you go isentropic. This is a TS diagram. Then isotropic expansion down to 2, typically high quality. Reheat, maybe up to state 3, the same temperature. It could be lower temperature at state 3 than 1. Expansion down to 4. Over here, condense at state 5. And where is state 6? Just a little above, and that's state 6 right there. Often you can't see it on a very difficult to see the difference between 5 and 6 on a TS diagram. Where is the waste? We just talked about, hey, it's great to bring in this heat into this working fluid at high temperature. Isn't all of this heat coming in at relatively high temperature? But where's the waste? There's more heat being brought in here. But when you're coming out with 6, we threw some numbers around. Let's say it was a temperature of 60 degrees C temperature at state 5. What's the temperature at state 6? Around 60.5. It's very close to 60 degrees C at state 6. And so we threw out some numbers. If you boost it all the way up, and it's going to start boiling at around 300 degrees C. I was using 8 megapascal for that boiler pressure. It's around 295 degrees C. And yet this temperature down here is 60 degrees C. There is a lot of heat addition at low temperature. Is it good to bring in heat into your working fluid at low temperature? No, not at all. So the regenerative strategy is to attack right there. And you say, that's pretty simple. Let's add a heat exchanger right here into the cycle, and let's warm it up, right? Let's add some heat to it. And so now the water going into the boiler or steam generator is warmer. It's not 60 degrees C, it's warmer. Well, how is this system going to work? There's a number of design options. You can, if this is burning coal to make it hot, well, you could burn more coal. But did that really help if you just burn more coal to preheat the... No, that's not going to help. Maybe you say, let's use solar. We'll have solar collectors, and we'll pipe it outside into a big parking lot filled with solar collectors, and we'll put our water through all these, parabolic trays, tubes. It would work, but nobody's doing it because we need the power plant to run not only in hot days when the sun's up, but we need it to run at night as well, and it wouldn't work so well. True? But that's an idea. Somebody says, burn something that's really cheap. All right, what's really cheap that we can get a lot of, we can burn? Agricultural waste, trash. Sure, that would work. That's probably more viable than a lot. But unfortunately, when you burn household waste, people don't want to be downwind of that. They don't want to be downwind of coal-fired plants, but they sure don't want to be downwind of a... Because guess what gets thrown in your trash? You know it gets thrown in your trash. Even the stuff that says don't throw in your trash, put it, recycle it. No, you throw it right in the trash. Batteries, things with a little lead, things with a little mercury, things that pharmaceutical pills and stuff, you just flush down the toilet or you throw in your trash. Anyway, no, probably not a great idea. It's not a lot of power plants doing that. So how do you make it work? How do you get it to be a little warmer? And what they call this is the feed water. They want the water that's feeding the steam generator or boiler to be warmer, not come in cold at 60 degrees C. So, what do we want to do? You want to take out of one pocket and put into the other pocket. Basically, when you split that at state 2, it's still pretty hot, and you can do something with it, okay? So what you can do is you can break it down here and bring it down to what they call a open feed water heater. And that's the strategy in regenerative vapor power cycle, okay? All right. So coming out at state 6, you mix with the fluid that's diverted from state 2, and you come out at a new state 7. But if you're going to mix it, it's just an open heat exchanger. You're just mixing 2 streams. Can you tell me a little bit about the pressure at 6 compared to the pressure at 2? Would it be greater, less than, or equal? It would be equal. And then, how about the pressure at 7? It's the same. They're all 3 the same pressure. But we know that the pressure at 2 is less than the pressure at 1. So what do I need to put between 7 and the introduction to the boiler? If the pressure at 1 is high compared to 2, and 2 is 6 is equal to 7, I need to put another pump. So you have now not only just pump number 1, you have 2 pumps to make the system work. So after the pump, you really have another state, state 8. So instead of having a system with 6 states, how many states do we have? 8. And one thing that'll really help you is get the pressures. Which pressure is high? The highest pressure in the system. Pressure 1 is equal to pressure at 8. What has the intermediate pressure? And then what has the lowest pressure? So this is the high pressure. We have the intermediate pressure and the low pressure. How about the low pressure? Where's the lowest pressure? Pressure at 4. Pressure at 5. Any other at the condenser pressure? So the intermediate pressure would be pressure at 2. Is that also 3? Is that also 6? Whoops. Is that also 7? Did we take care of all of our states? So even without calculating temperatures and enthalpies, you can get the pressures at all your states. That helps because all it takes is 2 intensive properties and it fixes a state. A lot of times pressure is one of them.
Are you really saving enough energy powering another pump for like heating it up?
Yep.
It's worthwhile?
Yeah, we'll compare the numbers. And I want you to do that too. I want you in your homework as well as studying to actually run some numbers and compare them. And yeah, it's pretty startling, isn't it? Because you would think, hold it, you didn't take anything from outside the system. You just rediverted something from inside the system, and it has a huge payback. All power plants do this. Yeah. All right. So let's think about this. What was the description of the fluid at state 5 going into the pump? It was saturated liquid. All right? What do you think the description of state 7 is going into the pump? Saturated liquid. And that's going to be key because a lot of students won't figure out, oh, state 7 is just like state 5. It's saturated liquid. That's where we want it to be. Because we can't feed two-phase liquids vapor mixture into a pump. It doesn't work very well. And there's no sense condensing it and throwing out more energy and making it subcooled liquid when saturated liquid is incompressible and it runs perfectly well in a pump. So this is saturated liquid. Well, if you got all that and you're able to analyze the previous system, this is pretty straightforward.
Why wouldn't you take the fluid coming out of turbine 2 and put it in the water heater?
Well, it's also at the very low pressure. And for an open feed water heater, the inlet has to have the same pressure. So you're at 20 kilopascal. Yeah, so you have to have it at some intermediate pressure. Well, we need to talk about our mass flow rates. What's special right here, it's nothing too complicated. You're splitting the flow, aren't you? So it's split right there. What's happening right here is you're joining the flow back together, true? So if we can trace out one stream which says the stream that continues on the loop, it goes over to this reheat. Then after reheat, it goes through this turbine, through the condenser, through this pump, and then into the open feed water heater along that path. So we'll talk about maybe the mass flow rate that goes to the reheat, or the mass flow rate that goes through the second turbine, or the mass flow rate that goes through the condenser, or the mass flow rate that goes through the pump number 1. But if I have, 11 kilograms per second flowing through reheat, then that I have the same magnitude kilograms per second going through the second turbine, condenser, and first pump. The other is what is split off this and gets diverted down here. Now this is not rocket science, I'm just going slowly over a mass balance. We have to get the mass balance correct. And then the other is after it's joined together, right here, it goes through the second pump and then through the first pass of the steam generator and then through the first turbine. Does that make sense? So we really have 3 distinct mass flow rates. So the other mass flow rate is, let me just write it down, the mass flow rate through the second pump, mass flow rate through the first pass of the steam generator, and the mass flow rate through the first turbine. And then the last one, there's really not a good subscript. I'm making a lot of these subscripts up. I don't think the book uses this many subscripts, but I'm trying to be clear about it, is the mass flow rate of steam that's diverted to feed the open feed water heater. And so this is the amount that's to feed the open feed water heater. All right. Now, from conservation of mass, both in the splitting and the joining, we know, well, typically we focus on what is the mass flow rate through the first turbine stage, what's the mass flow rate that feeds the open feed water heater. All right. So what we have is a mass balance. If you wanted to, in the splitting or the joining, what you find is that the mass flow rate that goes to the second turbine plus the mass flow rate that goes to feed the open feed water heater, that has to be the mass flow rate that went through the first turbine. That's from a mass balance, is that not? Does that make sense? Okay. Well, once you get all the mass flow rates down, they like to talk about fractions or percentages that go. So if this that goes down here is, let's say, 20%, if 20% of the fluid flow is diverted down, what percent continues on the long loop? 80%. This is not that hard. If it was 25, it'd be 75, right? But they both have to add up to 100%. So what they'll do is they'll take this mass balance and divide the whole thing by m dot T1, m dot T1, m dot T1. Well, it's equal to 100%. What is the sum? Well, this is the percent or fraction that goes to feed the open feed water heater. That's given the symbol Y. So they used the symbol Y instead of X. Well, X would have been a collision. What's X in thermo? Quality, right. So Y is defined as the mass flow rate that goes to feed the open feed water heater that's, diverted. It doesn't go into the second turbine or reheat, divided by the mass flow rate that goes through the first turbine stage or into the first turbine. They'll use some terminology like that. That's what Y is. And then this term over here, m dot T2 divided by m dot T1, well, it's not given another symbol, because you can see that if you wanted to calculate that, let me try and draw it down here. If somebody said, calculate the mass, well, let me do this. Mass flow rate that goes through the second turbine divided by the mass flow rate through the first turbine, that's 1 minus y, isn't it? That's just like we were doing, oh, that's 20%, then that's 80%. And then you will use this equation, actually more often than you think. Maybe somebody says, I want to know the mass flow rate going through the condenser. Well, what is that? That's 1 minus y times the mass flow rate that went through the first turbine. And we're going to use this equation in just a second. It almost seems too trivial. You're just little itty-bitty manipulations, algebraic manipulations. But is this equation readable? Does it make sense? All right. Let's press forward then. But all of this page is all on mass balance and introducing that term y. And a lot of times you'll see me, I'll say, for what the split is, I'll say that's y. And then this over here is 1 minus y, 1 minus y, 1 minus y, 1 minus y. You know, that's the fraction that goes through the pump, the condenser, the second turbine, the reheat. And then it's joined back up to 100% that goes through the second pump, 100% that goes through the first pass of the steam generator, and 100% that goes through the first turbine stage. How can I determine how large y needs to be for this open feed water heater? Somebody says, well, y is 19.3%. Okay, well, where did that number come from? So I'm going to pause for a second, and I would like you to work on this problem to develop the equation for y and be able to explain it to me as I walk around. Like, this is what I'm doing in order to calculate what y needs to be for this problem. And y will depend on what is the pressure of the steam generator, boiler, what's the condenser pressure, what's that intermediate pressure, what is the amount of superheat coming out of the steam generator, what's the value of the temperature coming after the reheat. Well, let's see, a couple jokes. You want a joke? How many people took Texas history? You know, it's a college level requirement to graduate, blah, blah, blah. Yeah, I did too. One of the things I learned was that there was a governor named something Hogg in the history books of Texas. Do you remember Governor Hogg? I forget what years he was, 1910 or 20 or something. And he had 2 daughters. And he named one of them, does anybody know this? Ima, so that she would say, who are you? I'm a hog. And then the other one is You're a hog. True. Anyway, I named my 2 daughters MB and EB, so I just wouldn't forget. That's what I named them, MB and EB. You know what MB stands for? I didn't name them that, but mass balance. We don't want to forget it. We don't want to forget it. We hardly use it, but this is one of those days we need it. It's pretty trivial, is it not? So what we do is we introduce a control volume. Well, I think the action's right here on that open feed water heater. And if I have a mass balance for that open feed water heater, I need to have some syntax for the subscripts. But I would say m dot through the second turbine, because that's what goes through the condenser through the first pump, plus the mass flow rate that's diverted to feed the open feed water heater is equal to the mass flow rate that goes through the first turbine. Well, it also goes through the second pump and through the first pass of the steam generator, right? Now, let's leave that alone for a second. Let's now combine it with an energy balance for the same control volume around the open feed water heater. What is the energy balance? I'm going to pause, walk around. So let me kind of help here a little bit. What do we have for an energy balance? I know that you can start with a control volume and the rate of change and neglect kinetic potential, and there's no shaft work and no rate of heat transfer outside the control volume to the environment. And it boils down to the mass flow rate coming in, and that stream coming from pump 1, which brings with it its enthalpy at 6. Did I do that right? M dot T2 is the same as M dot condenser, M dot pump 1, right? Plus the mass flow rate. I don't want that to look like a negative sign. The mass flow rate coming from to feed the open feed water heater, bringing with it its enthalpy at state 2. It's a little confusing. Somebody said, well, what's the enthalpy of the steam going then over to the reheat that enters into the reheat right there? What's that enthalpy? It's also 2. It's also 2. Okay. But that has to equal the mass flow rate that comes out, goes through the pump 2, goes through the first pass of steam generator, and it goes first turbine stage, and with its enthalpy H7. Now we have 2 equations, and you can do some manipulation. You can also, how do you want to do the simplification? You can divide the whole equation here by M dot T1, M dot T1, M dot T1, and you can substitute this right here from that equation. You could substitute that's M dot T1 minus M dot open feed water heater. I know I'm doing a couple steps at one time, but I would get an equation. You have more space than paper. You would go a little slower, and you would get 1 minus y times H6 plus y times H2 equal to 1 times H7. And then we do a little more algebra. Y is equal to H7 minus H6 divided by H2 minus H6. I know I checked a few people. Did you have every subscript correct on this definition of Y? Yes, yes, yes. 3. How many other? 4. You had it perfect? Because you can easily have a subscript off, right? There it is. Where did that equation, where did it come from? Mass balance and energy balance around the open feed water heater. And notice that, remember, state 7 is going to be dictated. It needs to come out saturated liquid. All right. Words can be very confusing. This is possibly one of them. So let's just read it. The question may read something like, determine the heat transfer from the working fluid, right there. What do they mean by the working fluid? It's the fluid that's going through the different components. It's the fluid going through this component, that component. Okay. Passing through the condenser. So now it's only the working fluid going through the condenser to the cooling water. Well, what's to the cooling water? The heat transfer. This is actually modifying the heat transfer. So it says, determine the heat transfer from the cooling water going through the condenser that is being transferred to the cooling water, which is some sort of lake water like this. So we have some lake water. You can think of lake water. It can be river water, a bunch of different things. But it has a temperature in and a temperature exit. And isn't there a transfer of heat between the two? And this is a great Q dot right there. So thinking Q dot is out of the cooling water going through, out of the working fluid going through the condenser and into the cooling water like that. Okay. But they want it in these units. They want it per kilogram of steam entering the first turbine stage. This is the confusing part. The rest of it was pretty good so far, but it's per kilogram of steam entering the first turbine stage. Well, if you do a control volume, the condenser, which you do have a Q dot out of it because the control volume doesn't cut way over here. It's not cutting the inlet and outlet of the cooling water. It's cutting between the heat transfer between the two fluid streams. You'll find that this Q dot is equal to the mass flow rate through the condenser times the enthalpy 4 minus enthalpy 5. Do you agree? So if you take this equation and you modify, you have q dot divided by m dot through the condenser. That's like lowercase q in the condenser. And that's h4 minus h5. But this will be kilojoules of heat transferred from the working fluid per kilogram of fluid that's going through the condenser. But they want it not per kilogram of fluid going through the condenser. They want it per kilogram of fluid going through the first turbine. So either we think back here, what was the relationship between the mass flow rate of fluid flowing through the condenser and the mass flow rate of the fluid going through the first turbine? So there is that. So what we do is we bring it over here and we say, we could write Q, here, let me write it like this, which is 1 minus Y times the mass flow rate through the first turbine times H4 minus H5. Do you see that substitution right there? Did that make sense? So now they want you to calculate Q dot divided by M dot T1. That's Q dot in the condenser is equal to lowercase q in the condenser, which is 1 minus Y times H4 minus H5. That's what they really want, because now it's per kilogram of the working fluid that enters or goes through the first turbine stage. All right. Why does it appear to be so confusing? Because then everything can get on the same per kilogram when you do an energy balance and for each component, you know, the works and the heat transfer for each component. Because when I put in a little bit of work here, all I have to do is boost the pressure of the fluid going through the condenser and through that first pump. The work that I get out of the second turbine is per kilogram of fluid going through the second turbine, but I may want to combine it with the net to calculate the net work of the cycle, and I'll put it on the basis of what goes through the first turbine. All right. So here's a problem. I see I have 4 minutes left. I ran out of time. How come I was a little faster at 9 a.m. than at 1 o'clock? I don't know. At 9 a.m. versus 1 o'clock. Pardon? Yeah. All right. So she's helping me here, reminding me. How do I solve a complex problem like this? Step 1. What do? Get a schematic. And the schematic needs to have components and states clearly shown. I need all the components. How many pumps do I have? How many turbines do I have? Do I have reheat? Where's the condenser? Where's this feed water heater? And then I need the states on that diagram. Okay, so the diagram with the components and the states. Not any small matter from a word problem. The next, what do? Give a diagram, a temperature entropy diagram. Where are all of these states on a TS diagram? That will help you immensely. And I don't have enough time, but I have a TS diagram for you today. I was going to do that. And then after I have a TS diagram, then you have a shot at getting a table full of properties. Table full of props. And the most important list or column is the H's. I need all the H's, enthalpies. All right. Well, I may use quality and entropies and this and that. Then I get a table of transfers. What do you mean transfers? The Q's and the W's. In this case, I like to work with lowercase q and lowercase w, but things have just changed when I have an open feed water heater, when I have a regenerative cycle, because it splits. And so I'll actually have what I call Q asterisk and W asterisk, where these are per kilogram going through the component, but these are per kilogram that went through the first turbine. And then I have my metrics that I calculate, the backwork ratio and the thermal efficiency. You really have to do this all by yourself. I do have 2 minutes. Can you please show me where each of these states would be on a TS diagram? There's a TS diagram. And we didn't change anything. How many states did we have?
9.
We have 8, 9, and 10 I use for diagnostic, looking inside what's happening. But believe me, you asked the question, is this really going to be effective? Well, here, if you look back, 35% of the heat was used to just heat the water up to the boiling point. Now, because it's coming in a lot hotter, only 22% of the heat is used to bring it up to the boiling point. Because it's not coming in at 60 anymore, it actually comes in over 180. And that's why. And there's no external additional use of any fuel or anything. It's just piping inside. So I guess I'll stop and not ask you to put them all, but please work to put them all on the diagram like this. And people are going to have a hard time with that very last state, state 8. Thank you very much for your attention.